So, the one sort of so one important thing that's happened is that there's been a lot of progress in at the intersection of quantum information and quantum gravity, right? We've understood like you know how various quantum information complex concepts from error correction and entanglement entropy to complexity apply to semi-classical gravity, and also how they can be used to solve stuff like the black hole information paradox. But one thing that does happen sometimes is that the actual the way it usually goes is that people prove some theorem in quantum information, okay, and then like there's one bit of the theorem that kind of resembles something in gravity, and then they say, okay, therefore we can apply this theorem to gravity, okay. And one of the things I'm interested in life is to kind of make this a little less abstract, make this a little more concrete, and like the way I want to do it is to actually take these quantum information concepts and directly put them in gravity, not like there's no analogy, no metaphor, okay. Of course, analogy and metaphor will be there for various reasons, which we can get into in the discussions, but to minimize them. So, one main focus, at least for the two topics that I do have planned, is a famous theorem by Harlow. Okay. What this theorem says is basically in a quantum error correcting code, okay, QECC means quantum error correcting code for me. What is known as the JLMS formula, I will explain what these words mean soon, is the same as subregion duality is the same as the RT formula.
So in this topic we use the term theorem literally.
This is a true theorem about quantum error correcting codes.
Quantum what?
Error correcting codes.
JLMS formula etc. have nothing to do with quantum error correction, right? I mean per se. That's
Right.
some holography and all that.
Okay, all of these have.
We already don't know how to write a quantum field theory. We don't know the definition of that.
What?
Right? I mean theorem is usually reserved for some mathematical.
Yeah. Sorry, I'm going to. This is the. If you wish, this is the.
Nothing to criticize. I'm just asking. That's the.
No, no, yeah.
That's the context in which you are using the word theorem, right?
No,
it
no.
could have been just a theorem in QECC.
It is a theorem in QACC, and I will write the more formal theorem right now in a minute, but I just wanted to like to say what the idea is. Yeah. This is not a theorem statement.
Yeah.
Okay, there is a real theorem, and this is not the statement.
I mean, you could say that JLMS and RT in philosophy are souped up versions. I mean, these are like toy versions of the real RT and the real.
Sure. Yeah. Yeah.
It's still not a theorem, right? What is the theorem?
There's a theorem in quantum error correction. Now, and there is an analog of the Takayanagi formula.
Yeah.
Yeah.
Okay.
To that extent, it's a theorem.
Okay. Anyway, let me just tell you what the theorem is. Okay. So.
I'm asking because I've been writing some papers on this subject and I don't know how liberal I should be with the word theorem. Just to learn.
I typically I'm not very liberal with the word theorem. Okay, I have in fact clashed with co-authors who want to say we prove that, and I want to say we argue that. Okay. Okay. So let's say it varies from person to person. Some people use it more liberally. It's fine. Okay. So consider so this figure here, weird squiggle is math cal small h. Okay. So consider a code subspace which consider a Hilbert space which splits into a direct sum of various tensor products over two subsystems little b and little b bar. Okay, and we will call little a b to be the set of linear operators acting on little h b alpha, say a b alpha, and we'll denote by a the all of the different a alphas acting on the various blocks. Okay, and consider a QECC which is a
What is that letter? Sigma or B?
which one?
No, the subscript, yeah.
B comma alpha,
B comma alpha and tau comma alpha.
B bar comma alpha.
Oh, B bar. Okay.
Yeah. Okay. VH code. So we'll take this to be an isometry for this theorem to H. Let me call this H physical. Okay. So I'm going to use anything which relates to codes and bulks. I'm going to use small letters. Anything which relates to physical Hilbert spaces and boundary Hilbert spaces, I will use big letters, which unfortunately makes me have to write this small h, which I'm very bad at, but I won't write here. So given an isometric QACC, so V dagger V equals the identity. The following are equivalent. Okay, and this is also not exactly Harlow's theorem, but it's close enough that we'll allow it. There exists some R star which maps the algebra of the code to the algebra of what do you say? So H phys has a tensor product decomposition into capital B and capital B bar, and we'll denote by capital A all the operators acting on capital B. Okay, L here means linear functions of. Okay. Okay, so there exists some map from the algebra on acting on little b, which is this guy, okay, to the algebra acting on capital B, okay, such that V A psi equals R star A V psi. Okay, for every
Sorry, this linear operator acts on the H physical, which is direct product of HB and HB bar.
Yeah.
Is it sum of or like?
This is a directed. This is just like a single tensor product.
And when you add this linear operator on the full, what will you get? Is it sum of B plus B bar or?
So what do you mean?
Like linear operator acting on HB.
Okay, so this R star A is acting only on HB. It is identity on HB bar. Okay. So okay, so this is known as subregion duality. Okay, which basically says that a sub algebra in the code, which is this little a, is equivalent to sub algebra in the physical Hilbert space. That's R star. I apologize. Yeah. Huh? Yeah, there exists a channel R star which does this. Yeah, it takes operators to operators. It's like you can think of it as a 4-index object. Like operators are 2-index objects. This is like a 4-index object.
This is true with some conditions on the B, right?
Isometric and yeah, no, the following are equivalent. So if this is not, see, given this much, this is not true. Okay, given this much and
You're right, we are finishing yet.
yeah, there are three things that are equivalent.
Okay.
If one of them is true, all the other three are true.
Yeah.
Other two are true. Okay, good. So take two states in the code, reduce them to the algebra A. Okay, what it means to reduce to algebra is not super important. It's like reducing it to a subregion. The relative entropy between those two guys is the same as the relative entropy between their images in the corresponding states in the physical Hilbert space.
reducing to the algebra means you get a density matrix first for
Yeah.
your state,
Yeah.
and then you get from it whatever the corresponding thing which computes all the expectations.
Yeah, that's right. Good.
And lies in the algebra.
Yeah.
etc.
Yeah, exactly. Yeah. This is known as the JLMS formula. Though, as Abhijit correctly pointed out, it is not really a JLMS formula, but whatever.
It's not JLMS because we don't have the bulk and we don't have the RT surface and we don't have the.
That's right. Yeah. So that's right. Yeah. Okay. And the final one is that if you have because your H code has this particular form, that means that every state in H code looks like sum over alpha square root p alpha psi alpha on b bar alpha. So it psi alpha lives in H b alpha tensor H b bar alpha, and it's a sum of those guys. That's what every state looks like this, and the image of that state under the encoding has to look like look very similar. The sum over alpha square root p alpha as before. Then there is psi alpha in b1 alpha, b bar 1 alpha, okay, where chi alpha. So here b alpha, so HB has been written as sum over alpha HB1 alpha tensor HB2 alpha, and similarly for HB bar. Okay, and the point is that these chi alphas do not depend on the code state. Okay, they are like degrees of freedom that you cannot touch from within the code. Okay. Okay, and then when this is true, that means that S of V psi restricted to B, the entanglement entropy, has the form of okay. So this here should be V psi. Okay. So it's the sum of a expectation value of a linear operator and something that's genuinely entanglement like, entropy like.
I'm a bit confused. Psi is a general state lying in your code subspace with various amplitudes, P alpha. So alpha denotes just some sum over states in the code subspace.
Yeah, it's like the different sectors of your code
But
space.
does it denote that?
Yeah, it's the same alpha.
Is the same alpha?
It's the same alpha.
Okay, so that wasn't clear. Okay.
Oh.
And then the isometry pushes this into the physical Hilbert space,
Mhm.
and psi alpha capital B alpha B bar alpha. Okay.
So this is the same psi alpha here and here.
It's the same thing.
Yeah, and this chi alpha is a new state, which is like some background entanglement in each alpha sector.
Each alpha.
Okay.
Sorry, Ronak, just 1 minute.
Yeah.
What is the context?
Okay, so I am just kind of reviewing Harlow's theorem about relationship between JLMS, subregion duality, and RT formula. The idea being that like I want to kind of basically what I say will hopefully make my point clear. Anyway, but let me just say that this here P alpha is a projector onto the alpha subspace, onto this alpha subspace. Okay, and so this guy is an operator, and this is an expectation value of an operator. This guy does not depend on the state. Maybe I should call it P hat alpha 2. This is a small p, that's a capital P. Okay. So here you have an expectation value of an operator, and then here you have something that looks like, you know, there's a Shannon entropy and there's a normal entanglement entropy and so on. Okay.
And what is SE?
SE means entanglement entropy. Yeah.
Just to understand the second line there, if I change my psi alpha,
Mm-hmm.
so I'm changing.
You're going to change So if you change only the psi alphas, keeping the p alphas constant,
Right.
you are going to change only this part.
You're only, just before that line even, in the previous line, you change your, of course, psi alpha, b, capital B alpha, B1 bar alpha,
Yeah.
but you don't change chi.
Yeah, chi alphas are stated, like there are degrees of freedom that the code cannot touch. It's always in the same state independent of code. Okay?
Sorry, this is the definition of psi alpha and chi alpha? I don't know.
Yeah, chi alpha is defined here.
Or is this a statement being made in the first two lines or the statement
Okay.
just made being in the last line?
Okay, it's good. So this is always true. This is just that rewritten. The non-trivial statement is that V psi looks like this.
V psi, and what is special about this? I mean,
Like
it looks like this. Not every state looks like this.
yeah, not every state looks like this.
Okay, in what sense?
It could have been that the new state could have depended on psi alpha in some, or p alpha in some non-trivial way. This is a special state where you have HB is sorry H.
Wait, I can always do that, right?
No, there's actually something very non-trivial here because
The fact that the square root p is the same as square root p there. Is that the point?
no. Let me just so
The fact that little b is encoded in capital B.
yeah. So the point is H phase. So look here. So the point of H phase is that HB is equal to the tensor product of HB and HB bar. Okay. Now H capital B has all these alpha sectors. Okay. Similarly, H capital B bar has all these alpha sectors. So when you write this out, looks like plus alpha HB alpha tensor plus alpha prime HB alpha prime. So general state in H phase does not have to have the same alpha sector on B and B bar. Okay. Whereas the image of the code subspace does.
What was B and what was B bar?
Okay.
Huh? 2 minutes, just explain the notation.
Okay, fine.
if you don't mind.
Okay, fine. So the Harlow theorem is the following. Okay. So consider an H code which looks like a direct sum over tensor products. Okay.
Just H code means what?
H code is right.
Semi-classical.
I have not. No, this is about QACC. This is not about gravity. The whole point is that this is not about gravity. Okay. H code is like it's some set of simple stuff.
Single trace stuff. Okay. Yeah.
Sure. In some context. Okay.
Yeah, okay.
But like this is the point I want to make is this is a theorem about quantum error correcting codes in general, not about any. This is not about gravity. Okay. Consider some Hilbert space which can be written as a direct sum over tensor products. Okay. The different the two tensor products, the two subsystems will be little b and little b bar. Okay. And it's like not a tensor product of little b and b bar, but in general some direct sum over many of these.
In a gravity setup, this would be like two sides of an eternal black hole.
Yes, and the alpha would be like different areas of the horizon. Okay. Yeah. Now, and then there's some set of operators acting on each of these HB alphas, which I'll call little a alpha, and little a is just the it's just putting all the little a alphas. It's just the sum of all the different algebras.
What's the sum of algebras? Sum
Yeah.
of algebras.
Yeah. Yeah. It's just like it's a block diagonal set of block diagonal operators.
Okay.
Okay.
Sorry, that B is a label and alpha is also a label?
Yes. Alpha labels the sector, B labels the subsystem.
Sector and subsystem. In the gravity context, you can say what?
Alpha would be different values of the different macrocanonical windows.
Values, okay, so masses of
Yeah. Yeah.
Okay. And B would be with
Mm.
mixed
Right, yeah, the exteriors, the two exteriors. Okay.
Yeah.
Okay. Anyway, and then there's a quantum error correcting code which isometrically maps it into some physical Hilbert space, which is H capital B tensor H capital B bar. Okay.
Physical means boundary.
Sure.
Okay. Yeah.
See again.
I mean, you can be very abstract, but just
No. Yeah. Okay. This is an isometry. Okay. Now the point is that there are
it's B times B bar because there are two angles.
yeah exactly.
Okay.
Just to say, or you could just have one boundary, right?
And you can cut it up and yes.
Subspace
Yeah.
This is the thing Abhijit loves.
Okay. All that stuff is going to come tomorrow.
Okay, fine.
Okay. Or
Sorry, why is it block diagonal? Like you cannot change this.
the idea is that the left black hole and the right black hole have the same mass, Okay, and to change it, you really need to act by a two-sided operator, like a like a double trace deformation on the two sides and stuff. Those are the things that change the mass. So yeah.
Change the relative mass.
No, the mass of the two black holes is the same.
But you could imagine a mass on one side.
If you have a long wormhole, but we are in a code subspace without long wormholes.
Without what?
Long wormholes. Yeah, long wormholes allow you to have different masses.
Long wormholes is where this kind of thing happens.
Yeah. Okay.
A lot of stuff behind the horizon on one side.
Yeah.
Just that.
Yeah. Okay, good. Okay, so then in a general code which has nothing to do with gravity, okay. In fact, what I want to problematize is the relation between this and gravity. Okay.
But without the gravity, I won't understand.
Yeah, I know. But I'm really repeating this to say that I'm kind of trying to keep a distance between this statement and gravity.
Get.
Yeah, good. So there are three equivalent statements. Okay. The first equivalent statement is that you can take a operator acting on little b and make it an operator acting on capital B, and there is some linear map that does that.
Little b was which one? Capital B?
Little b was one of the code. Yeah. So all my little things are going to be codes and bulks. My capitals are going to be boundaries and physicals. Okay.
So these statements are kind of the statements that
Are equivalent.
What correspond to reconstruction.
Yeah. This is subregion duality. Okay. This is saying that.
The fact that the B is reconstructed in B itself.
Yeah.
Capital B itself.
Yeah, exactly. Secondly, the next equivalent statement is that the relative entropy of two states in the code is the same as the relative entropy of the corresponding states in the physical Hilbert space. This is known as the JLMS formula in gravity. Okay. Thirdly, and this is so every state in the code has this form, which it's basically it's got some probability of being in an alpha sector and some state in the alpha sector, and then the non-trivial statement is that its image. Okay. So these are the non-trivial statements. Its image also looks very similar, except in each alpha sector I added an extra state which is chi alpha. I always absorb them into like the definitions of B1 and B2.
No, but that unitary is the non-trivial encoding map. Right?
No, you can absorb them into the definition of B1 and B2. Like the Harlow's theorem is written in a redundant fashion. The unitaries are not important.
H physical also has a sum over alphas?
No. Yeah, so HB and HB bar. So each HB has a sum over alphas. Okay. And HB bar has its own sum over alphas. So if general state in H physical can be in a different alpha sector for B and B bar. Okay. But a code state has the same alpha sector on B and B bar.
There is no alpha, right? I mean, to begin with in the physical, this is just your creation. Or
Yeah, there is you can decompose HB in some way. Okay.
yeah.
Its value of a Hamiltonian, right? Alpha?
No, it's not quite, because it's a Hamiltonian minus bulk boost Hamiltonian or something. We don't need to.
But not the energy on the left and energy on the right.
No, because the boost energies of the bulk state matter. Like it's.
No, just in the field theory.
Yeah, no. But I'm saying that alpha is more like an area than a ADM Hamiltonian.
No, but it's not even like a alpha sector. Alpha is not the same on both sides, right?
It is. In the code state, it is. In the general state, it is not. Okay.
In the general state.
But even in a code state, you can send a lot of stuff from one side behind the horizon.
But it will never change the area. So what will happen is that, this is why alpha is an area. So you can say, oh, I'm going to throw a bunch of stuff in. It will change the energy, but the area is kind of untouched because space-like to everything.
Area at the
Horizon.
location.
Yeah. So this is I wrote an entire paper about the relationship between area and ADM energy and how that's like the relationship between this story and the type 2 algebra stuff.
Now I'm a bit confused because the encoding U, if you get rid of it, is this statement still true? Because that U
Yeah.
generally acts on the B's and Chi's, right?
You can think about the U as you can absorb the U into the definition of B1 alpha and B2 alpha.
Definition of B1.
Yeah, I mean, sorry, capital B1 alpha and capital B2 alpha. Oh, that's what you meant. Yes. Yeah, you can absorb it into the definition of these two factors. Okay, Harlow just says, okay, consider a simple form for the factors, but then like have a unitary, okay, which puts the simple things into the complicated encoding. But for me, HB1 alpha is not some simple thing. It's just some complicated subfactor.
So in the ATS CFT context, what is B1 and what is B2?
Roughly speaking, this is the IR degrees of freedom that this is the IR degrees of freedom that you can't touch from bulk operators. These are the UV degrees of freedom that bulk operators cannot mess with without large back reaction. Okay, if you touch these the degrees of freedom, you will create massive back reaction.
Is HB1 alpha isomorphic to small h?
HB1 alpha is isomorphic to small HB alpha. That is right. Thank you. Yes.
For different alphas, can you have different B's and B bars?
Yes. Oh wait, sorry. Capital B or capital B bar?
Small b.
Yeah. So small h little b alpha did not, like h little b1 and h little b2 might be very different Hilbert spaces. Okay, but it's important in this theorem that the boundary is just tensor factorizes in the normal way. Yeah.
That's that line, but now I didn't get
Now to go from here to here,
just explain the last line.
okay. So
Before that, the psi alpha just to use the same symbol, right?
yeah, it's literally the same state except in a different.
Literally the same state except for
Like the blade HBB, this Hilbert space and this Hilbert space are isomorphic.
The isometry is pushing you into
Yeah.
the physical Hilbert space.
Yeah.
Okay.
And all it's doing is it's adding some background state for every alpha.
Why?
Huh?
Why there is a B2 psi alpha state? I don't know.
Why there is this? This is the content of the theorem, which says that if you have this, it's this is the same as this is the same as this. Okay, this is a non-trivial statement that there's only this chi alpha pops up. Okay.
Sorry, I mean if you just linearity of V, put this through, then it is P square root P alpha stuff comes and then V acts there. Isn't this the statement that the psi alpha V acted on, you get this stuff, alpha by alpha?
Yes.
No, you need something more than linearity. You need the fact that okay, good. If you linearity of V and 1 second. Here you're very importantly using the fact that stuff is reconstructible, like you're using subregion duality.
That's what I'm trying to see where exactly, because that just seems that alpha by alpha you're writing general solution there.
Yeah, it's not. You could in general be mixed. You could take what this is doing is that it's making sure that the information in little b alpha is being kept in capital B, but without subregion duality that would not be guaranteed.
But where is it doing that? It's just the general answer. Just look at
This is
one
not a
alpha
general
term,
statement.
One single alpha term.
Huh.
Okay, let's forget that.
In a general case,
you can do that.
B1 alpha, like B1 alpha need not be inside capital B. Okay.
I thought that's the definition of capital B there.
No, I'm saying the statement is that HB can be written like this, such that psi alpha is in B1 alpha and B bar 1 alpha. Okay. So the statement is that like in general without subregion duality, linearity would just tell you that okay, like the full thing looks like this, but for some B1 alpha which need not be inside capital B. Okay. Whereas subregion duality is telling you that capital B1 alpha is inside capital
No,
B.
but the subscripts there is B1 and B1 bar also, right? It's not like you're making some statement about psi alpha. B1 bar also. What does that mean? Then it might as well erase it.
So B1 bar is a subset of B.
Yeah.
But he is insisting that it's somehow created in B, right? So how do I see that?
I don't understand your question. I mean, I'm just saying that.
Maybe Ronak, it's easiest to visualize if you just have like one alpha first of all. And
Yeah.
Let's just say you have, forget about B bar, little b bar. Let's just say you have small b, right?
Mhm.
Yeah.
So in that case, it's clear, right?
Yeah. Yeah, then you will erase those B bars here also.
Yeah.
Yeah, that's a
That's
statement.
clear, right? Yeah.
Yeah.
But here it's some general, looks like a general statement. And where is the.
It's not a general state because alpha and alpha, you have the same alpha sector on both sides. And also the information in little b is being put into capital B.
Where is that coming? This information in small b goes in the capital B.
Oh, okay. I think I have to say, I have to add the statement that HB is isomorphic to HB1 alpha. Now HB alpha is isomorphic to HB1 alpha and
Isomorphic means same dimension. How does that happen?
and yeah.
Isomorphism is just that.
Maybe that's where absorption of the unitaries goes into.
Yeah, that's where absorption of the unitaries goes into. That's true, but Okay, and let's just say that the restriction, what do you say? The map you get by restricting an alpha and tracing out the B2 and B2 bar is like is a unitary. Is a tensor is a factorized unitary. I can add something like that.
I mean, it's clear from this structure that if you erase capital B bar, then you will not lose the information of small b, right?
Yeah, how is that clear?
Yeah, okay, yeah, you're right. I have not made it clear in this notation, but it is true. It is a fact that I have not made clear in this.
No, but somebody is saying that it is clear. For
Yeah,
us.
if you just
No, he's a
think about it from the decoupling point of view,
Yes.
right? If you trace out capital B bar,
Yes.
your little b is entirely contained inside capital B. So even if you trace out capital B bar, you're not going to get.
no.
but
Abhijit's
we
point
can
is
do
that
this as well.
Abhijit's point is because I only spoke about little b bar and the combinations here. There could be something mixing stuff from little b into capital B bar, which is true. What I've said here does not preclude that.
If there's no small b bar, then it's there.
Yeah, if you just erase all those B bars, then probably it's
Yeah.
The
Right.
same thing,
I should have said a little more. Yeah. No, yeah. Okay, yeah, right. I should have said a little more about this.
In the usual Darcy Harlow lectures, there isn't a B bar.
Yeah, I think this is exactly why he doesn't
And
put it.
that's why it's
Yeah.
confusing.
Yeah.
At least for me.
Yeah. In the main theorem statement, he doesn't go to B bar, and then like he always has a next section where he puts it in. You're right. I should have been a little more careful about this.
Okay, but then what is the statement?
The statement is that basically the information in little b is put into capital
Yeah,
B1.
that's the statement
Yeah.
one.
Yeah. And okay, good. And so if you make this and, okay, so the two statements together, tell you, sir, we will tell you something, which is that the entanglement entropy of V psi has a piece which is just the entanglement entropy of original psi. Okay. Now this ensures that you are not moving information into B bar. Okay.
Just explain
Yeah.
the last line. So now the left hand side is the
And
relative entropy.
is the entanglement entropy of the image state V psi restricted to the subsystem capital B, okay, which looks like the entanglement entropy of the original state psi, okay, plus the expectation value of a linear operator, okay, and the idea is that this operator is often called the area operator. Okay, I will call it the information theoretic area operator, okay, which may or may not have anything to do with the geometric area.
So not always can you formulate the remainder piece as a linear expectation value of linear operator.
Yeah, this is a non-trivial thing.
But now SE chi A seems to suggest that it's a property of chi A itself.
It's the entanglement entropy of chi alpha reduced to B2 alpha.
Reduced to B2.
Yeah, that's right. Sorry, I should have put that in here.
Trying to understand.
Yeah.
I see.
Ah,
That's the statement.
yeah. And like, so it's just because chi alpha doesn't depend on state, this entanglement entropy doesn't depend on the code state. So you can just like put it as a number. Okay.
Is B2 some extra degrees of freedom?
Yeah, you should think of B2 and B2 bar as like some UV degrees of freedom that like you cannot touch in the code, like
From the gravity,
or like if you want to apply, you can apply this also to RG, okay, where code is like the IR degrees of freedom and physical is the UV CFT Hilbert space, okay, and then the point is that your low energy operators won't touch certain degrees of freedom in the UV Hilbert space, and then chi alpha would be those guys. The point is that this is a much broader set of theory. It has a much broader application. It works for RG also. Yeah.
So this linear operator, this depends only on the encoding.
This linear operator, yeah, basically because the V is the thing that knows about chi alpha, and therefore it depends on non-linear V on V. Because it depends non-linearly on chi alpha, okay, entropies are non-linear, but it depends only on V. Sorry, what? V is a linear operator. I'm saying that the area is a non-linear function of V.
Non-linear function of B.
Yes, because it's a non-linear function of chi alpha. Okay. So, and
Very sorry.
yeah, go ahead.
Excuse me, but you understand that the physical Hilbert space has this tensor decomposition, HB tensor product, HB
bar.
and then HB itself has, subspaces B1 alpha. And the entire structure of H physical is sum over alpha H B1 alpha tensor product H.
Okay, so let me just write out.
Alpha is that a statement?
Maybe I'll just write this equation out.
Just trying to understand
Yeah, so good. So H phase, okay, is equal to plus over alpha alpha prime
Okay.
HB1 alpha
Now I'm getting it slowly. Okay.
HB2 alpha, slightly bigger tensor factor, HB1 bar alpha, tensor HB2 bar alpha.
Sorry, so this
Sorry, it's alpha primes on the right, alpha primes.
why? So this alpha stuff was something that was defined in H code, right?
Yeah.
Why is that the same alpha that appears there? I mean, I can just now take an isometry from that Hilbert space to anything I want.
Yeah.
Why does it guarantee that the set that I mean, the vector space that I go to
Mhm.
has to
So
have this structure
the
with
isometric,
same
the-
alpha
the-
values and so on?
So take two states and different alpha sectors in the code. Okay, they're orthogonal in the code, and because it's an isometry, they have to be orthogonal in the physical Hilbert space also. Okay, therefore, from this you can construct different alpha sectors in the physical Hilbert space. Now you're right that this is not the most general. There could be some remainder term here. Okay, but I'm just ignoring the remainder. Like I'm truncating to the physical Hilbert space to the part that participates in the code.
So this in particular H beta alpha you can define separately as image of
Yeah, HB alpha.
image of H B alpha.
Yeah.
And now, sorry,
Mhm.
the isometry pushes both subspace states into direct sum HB1 alpha tensor product HB2 alpha.
Yeah, with the same alpha.
Same alpha. Same
But
alpha.
general state is not the same alpha.
It is not the same, but but the isometry is not touching B bars, right? Oh,
So it's touching B. It's touching everything.
it's touching every.
Like it's mapping little b into capital B and little b bar into capital B bar. Yeah.
What does alpha mean from B2 point of view?
So like for example, if you have two CFTs, you can consider states with one area here and a completely different area prime here, right? Like you can consider like factorized black holes. But then the statement is that the code subspace is things where you have the same area, and you have a
So that is B and B bar, right? Not B1 and B2. I was saying like
but B1 and B2 are different.
B1 and B2 was like you said IR and B.
Yeah, that's right. That's right.
So then what does this decomposition alpha mean for B1 and B2?
That means that this alpha is some part of the UV information that you can actually access, but you cannot change from one side. Okay. So like the area is it knows it's some manifestation of the UV, because area tells you about the entanglement of UV degrees of freedom.
H phase and HB are the same.
H phase is HB tensor HB bar. Okay.
Ronak, if one last thing, in point number 3, if I take two states in the code subspace,
The chi alpha is the same. The chi alpha does not depend on psi alpha.
that's what I thought. But now, in psi, which is a sum over psi alpha, that alpha is a sum over different states in the physical.
This is
code subspace.
yeah, this is an H code, yeah.
So, if I take psi 1 and psi 2 in the code subspace with some square root, never mind, then won't I get chi 1 and chi 2?
No, you'll get the same chi alphas. The only thing you can do within the code is change the relative weight of the different chi alphas by changing this probability distribution here. Okay, from the code, you can't actually change these states are kind of untouchable. Okay.
In some sense, this is really the content of point 3, right? Like this
That is the content, yes. That you have these chi alphas really
They are just the same.
for all code states, yeah.
The psi alphas, of course, change around in B, capital B1 bar, but chi alphas don't change.
Yeah. Again, you should. I think I like to think about this in RG actually, because it's very clear in RG that like you act with low energy operators, you're never going to change like whatever's happening at very very short distances. So this is very clear from the point of view of RG.
So B2 is not accessible at low energies.
It is not accessible at low energies. Only one. Yeah, exactly. The only UV degree of freedom that you can access is like alpha, which is telling you something about the UV degree of freedom, but it's not. So like in gravity we know entropies, but we don't know microstates. This is formalizing that statement, because here the microstates are in chi alpha of the entropy, but we can calculate the entropy because we just need this guy. We just need one piece of information about the microstates. Yeah. Okay. Cool. The point is that this is entirely about quantum recurring codes. Oh yeah, is there anything else we want to talk about with this?
Sorry, you said that B is a linear function of chi.
So
B is a linear function of chi, or
V is a linear function of chi alpha. Yeah.
and so this is not linear because of SE.
Huh? Huh? He's asking about V.
But V is this
V is a linear function of chi alphas.
My question was about why you said SE is a non-linear function of chi alpha. Chi alpha is because of SE, right? Not because of U.
Yeah, SE is chi alpha log chi alpha. So yeah.
I see. So this should be thought of as actual entanglement entropy of this guy,
Yeah, of the chi alphas, yes.
of the chi alpha.
But the point is that low energy theory only knows about the entanglement entropy of the chi alpha, doesn't know about what the state chi alpha is.
I see. So no, in this formula, when you call that A hat as a linear operator, I should think of those to be actual coefficients, numbers,
Yeah.
which are multiplying projectors.
Yes.
I see.
Yeah, so it doesn't depend
I
on
see.
the
So
code
you
state.
actually know what that area operator is.
Yeah.
It's a projector with those coefficients.
Yes.
I see. Thank you.
Yeah.
Slightly, if you're thinking in terms of not being able to change A hat, then you mean you're not changing the square root of P alphas.
No, the square root of P alpha goes into the expectation value part.
So you will change that.
Yeah.
So it depends on the physical state
Yeah,
of
exactly.
energies, but to some
Yeah.
limited extent.
Yeah.
Is there any simple reason why these three statements are equivalent?
It would take like half an hour at least to go through the proof.
Are you going to go through it?
No. No.
That leaves us.
This is Harlow's theorem.
This is Harlow's theorem, slightly simplified.
Usually it's slightly more simply stated, I would say, because you don't have the B bars and you know.
Okay, fine. It's the part. It's Harlow's theorem in the way that you actually think about it in ADS-CFT and then simplified. Okay. Yeah. Fine.
Was there anything which is remotely similar that was known before in quantum information literature?
There was, but what? In fact, like various bits of this were known. Harlow put a lot of them together, and the operator algebra quantum error correction, which is what this is, did exist, but this specific theorem putting these three things together did not, I believe. In particular, this condition was inspired by ADS-CFT. The JLMF formula. Is that wrong? Huh? Huh? What's going on?
I mean, it's basically in information theory, people call this what do you call it? The information process, data processing inequality, right? The saturation of the data processing.
Yeah, but wait, that's true. But was this equivalence known before?
1-2 equivalence was probably not.
1 to okay, I haven't found it in the literature, but okay, maybe you're right.
But I think at least implicitly, it's known.
Implicitly, yeah, fair. That's fair. But definitely, like the RT formula part was not.
The RT formula part was, I think,
Okay, good.
the last statement.
Yeah, that's right.
So the left hand side you're tracing over B bars.
In the left hand side, you're tracing over B bar. Yeah, that's what this notation means. That like you're restricted to capital B.
So Ronak, if I instead of computing entanglement entropy, I compute let's say linear entropy.
That is, yeah. So the, matching that to ADS-CFT actually restricts this course to cases where these chi alphas are maximally entangled. This is a paper by.
I mean, let's say the first two lines are true, right? And then I want to see the Renyi entropy of V psi. Would there be a similar formula for Renyi entropy?
Yeah, so there is in fact a similar formula, but you would get a different linear operator for every n
Yes.
in
So
general.
would it be that P alpha weighted with the Renyi entropy of chi alpha?
Effectively, yeah. You actually have to look at the modular entropy to get this form, but yeah, close enough. Modular entropy is slightly different from any entropy, but more or less same.
When you are actually working this out, the implication from 1, 2 to 3, what special property of entanglement entropy that is being used?
What is the special property of entanglement entropy that is being used? It is the fact that the important thing here is that the entanglement entropy in some sense is like what do you say? Imagine chi alpha has like a huge amount of entanglement. The point is that in the Renyi entropy, this term would like the dominant p alpha, the dominant alpha sector in the in this term would be very different from the dominant alpha sector in the state itself, okay, because this would become exponential of a Renyi entropy, and
so these dimensions could be 5, 7, 8 and so on, right? What is this dominant?
oh yeah, sure, in a general QACC, you're right.
Yeah, general QACC, when you
Yeah.
want to get this third statement from 1 to
yeah, then you can actually I think you can for modular
unitary invariant I can put there on all the 3 terms.
you'd have to be careful, but I just like I think it works for
Any invariant that factorizes.
Yeah.
Factorized state is separate.
no, I think for any entropy you have to put a log of expectation value. I think for modular you have to be careful because I think you have to put the modular entropy and it works, but for any entropy it doesn't quite work. This here becomes a log of expectation value here. If I'm not wrong, I have to check. But
Nothing to do with factorization.
what is the total factorization? But any entropy is still factorized.
Invariant which, so the Renyi entropy has a log in it,
Yeah.
and that factorizes. Right? If you have a factorized state, you get the sum of the Renyi entropy. Right?
Yeah.
Is that not right?
I'd have to okay. I'll have to check here. Yeah. I know it works with modular entropy, which is slightly different from any entropy. It can be written as the entanglement of a different state, but I don't know. Like with Renyi entropy, I would have to check. It might there is a expectation value somewhere, but it could be log of it or something.
So in this formula, P alpha is the projector to an alpha
Sector, yes.
and you call it area operator, is it always?
I call it the information theoretic area operator. I will not call it the area operator. Yeah.
But do you get exactly area in the
That is one of my talks is about getting area and gravity side from this.
Two-sided thing like entropy of one black hole will be the entanglement, but here it seems like you have entanglement entropy, which is the second term, but then there is first term also which you are calling.
So this is the bulk entanglement entropy in ADS-CFT. The entanglement entropy of bulk fields goes here, okay, and this is the area part.
So SE by alpha you're tracing over assuming B1 and B1.
In SEK alpha, you are tracing over B2 bar alpha.
Style is in the two sides.
Yeah, chi alpha lives in this.
I thought you get the density. Okay. You get the density matrix with chi alpha, you're tracing over the others, and then you
I mean, chi alpha lives in this Hilbert space.
yes.
You trace out B2 bar alpha, you get a density matrix for one B2 alpha, and then you look at its fundamental entropy.
Okay. I see. And so it's similar on SE psi alpha, you're tracing over the bar.
Yeah, here you can think of SE psi alpha as living in B alpha, the original B alpha.
My one sentence summary for my benefit is you've taken Harlow, which had B1 and B1 bar, and added to it a UV sector, which is that B1 has some UV sector, B.
No, Harlow had the UV sector also. Didn't he have the UV sector in? Yeah, this is
But mostly it was just the region and the complementary. You know, you drew the RT surface, you had the region V, you have the complementary region, and then yeah, it could have been a sum over direct products.
No, so the direct sum was there in Harlow. The UV sector was also there in Harlow because he's the guy who pointed out that like.
The UV sector was there only because you couldn't divide one number by another or some silly reason.
No, that is a remainder Hilbert space which I threw away. I throw away the remainder Hilbert space.
But this was okay anyway. This wasn't quite there. I thought. I mean, you don't need it.
Was it there? It's there. I thought so too. Yeah. Okay, fine.
The area, right? I mean, it's important for the area.
It's the area, but okay. Yeah.
Okay.
I mean, you know, if you put it in there, then okay.
with the difference from Harlow is that I kept B bar, I kept the factorization of B bar also explicitly, like the decomposition. That's there in the next section. It's not there in the main theorem. Yeah, yeah.
When you go from, sorry, this is a technical, but B2, if you want to kind of imply 1, 2 from B,
Yeah.
then it's probably important that this holds for entanglement entropy, not ready entropy, right?
No, in fact, the actual theorem, which is TFAE, does not even have the entanglement entropy. I just kind of mashed stuff up in a slightly annoying way. In fact, it really just has this written in a slightly better way so that it's clear that the B information went to B1 alpha.
Just that.
Yeah, that's what. This is really, in Harlow's paper, he really writes a better version of this line, and then there's a next section which shows that this line implies this line. but like I just messed up this line, so I made
Just had this type of equality, you wouldn't be able to
no, I told
the reconstruction statement.
I don't believe so. No.
I thought you could, right? That's like a decoupling, and then you.
If you have just the entanglement statement and not the decomposition statement, can you prove 1 and 2? I don't think so.
That's decoupling.
Really?
You say you prove the vanishing of mutual information, and
I see. Okay, I haven't thought about this. Okay, maybe it's
then
possible.
you use the fact that it's really entanglement entropy, right? So that you have decoupling at your disposal.
I see.
So the last statement implies decoupling, which then implies quantum duck.
Yeah.
Part of the third statement.
Yeah.
Then implies everything else.
Okay. Yeah. Okay, I didn't realize you could just use this to go to decoupling directly. But okay. Okay, that's fair.
I'm really
Good.
sorry, but let me just get it in my mind. You have the little b and the little b bar, right? And the isometry takes, where is that statement? The isometry takes a general state, no, even before that. The H code is states which get pushed into a combination of capital B cross capital B bar, where capital B is this 4 tensor product.
Capital B is just 2 tensor products. It's this is capital B, this is capital B bar.
In the case that there was no alpha, as Onkar was explaining to me, this is mapped into some physical space, and then B2 is just whatever's left, right?
Yeah.
Just it's nothing deep. It's just whatever's.
Yeah, it's exactly.
It could be entangled. That's
What?
It could be entangled.
No, but just the Hilbert space decomposition. You've got some map, and then whatever's left is B2.
Yeah, that's right.
In the additive sense.
Yeah.
Left meaning to make up the whole space.
Yeah.
So it's not some deep thing.
And so that's what I'm just trying to fix, that the isometry maps into B1 cross B1 bar, right?
Like I mean.
Yeah, the isometry maps to B. Yeah, the map is to B1, and then whatever's left in H phys is B1, is B2. I mean,
Yeah.
in the left sector.
Yeah, exactly. Yeah.
It's nothing.
In the left, but
No, but left in the multiplicative sense.
Yeah. To make up the whole Hilbert space.
Left in the degree of freedom sense.
Yeah.
hey, but what's unclear to me, so sorry about this, is that you have capital B cross capital B bar, right? Capital B seems to have
These two pieces.
B1 and B1 and B2, right?
Yeah.
And the isometry maps a physical state.
So like the point is, think about a degree of freedom. Okay.
Full tensor product.
Think about as Shiraz was saying, think about the degrees of freedom. Okay, the little b degrees of freedom go into little b1, okay, capital B1, and then there are degrees of freedom that you don't need to put the state little b in. Okay, those are the capital B2 degrees of freedom, and they are in some fixed state. Okay, that otherwise this would not be a linear operator. If the leftover degrees of freedom were not in a fixed state, this would not be a linear operator. So you have to just make them in a fixed state.
But then what's B1 bar doing?
B1 bar is the information of little b bar.
So the code subspace is getting mapped to B1?
B1 bar.
Yeah.
Can we say there's like a natural isomorphism between B, V bar, V1, V1 bar, so that they
Yeah,
keep
that
the
is.
same state, just plug
Yeah, that's a natural isomorphism. That's right.
Okay.
Is there some redundancy in type?
What do you mean redundancy?
Like, can you have some different types such that?
That's a different code.
B1 bar. B2 is B2, B2 bar.
Yeah, that's it. Some codes, one code will have a fixed set of guys.
I would say is that I'm going to try with Onkar. So there's B and B bar, which in one context would be left and right
Exterior stuff.
exterior stuff. So if you are doing capital B's, it would be one CFT and the other CFT. That's B and B bar. Okay, we'll come to alpha in a minute. Forget about alpha first. B1 is all the single trace operators on the first CFT. B1 bar is all the single trace operators on the second CFT.
That's right.
Okay, then B2 is everything other than single trace operators in, as he said, degree of freedom sense.
Yeah.
Some UV stuff, whatever.
Yeah.
Where the whole CFT has a larger Hilbert space than things you can make out of
Yeah.
single trace.
Yeah.
Okay, B2 bar is what, everything other than the other.
On the other side.
Okay, this part sort of seems clear. Now alpha, which is more, for me more tricky.
No, but before that, okay.
Actually, maybe can I just can I interrupt this? So actually, my talk tomorrow is going to be about a very concrete realization of this. Maybe I can just do that right now. Maybe like take a 2D CFT and like recreate the structure,
Okay, you do
and that will hopefully make things clear.
Yeah.
How about that?
As you like, but just to say, okay, so we have B1 and we have B2, right?
Yeah.
And let's talk about just the ones part because the twos are not. Oh, sorry. Let's talk about the unbarred part for now, right? And then the encoding is from a from the code subspace to the B1 cross B2 parts, and the bars don't do very much.
B1 cross B1 bar. No, the twos don't do very much.
Oh, sorry. So that's the bar.
The bar is bar means complementary.
Enters in the encoding.
Let's say we're only interested in one of gravitons on one side.
Yes.
So we can forget about the bars for a moment.
Okay, great.
Okay, so we're only interested in gravitons on the right. Then the encoding is you take a state in whatever your fancy code subspace. That's the you take a state in the bulk and you map it to a state in B1.
Yeah.
Okay, but now that's just the map. But the full Hilbert space on the field theory has more than B1, and that's
Yeah.
the state in B2. In B2.
Yeah, that's right.
No, B1 and B2.
What?
Sorry, B2 and B2 bar.
No, let's
He's forgetting about one
But
side.
that, you cannot forget that for chi. That's
No, he's like go below.
but
Go
chi
to.
has to be the both sided.
Okay.
Otherwise, I mean, this,
Yeah.
this remaining part has to be both sided because that's the area part. Now,
Yeah.
even if your bulk excitation is on one side, the area part is measuring the entanglement between the two CFTs.
Yeah.
The vacuum state even, right?
The alpha, you're worrying about this alpha.
No.
No, the entanglement of the chi is an entangled state.
The
It's very
basic
important that chi
entanglement,
is an entangled state.
that has to be both
Okay,
sided, no?
and that has to be a two-sided thing. But that's fine because like it's not taking part in anything. It's just there. It's like stuff that you can't like mess with.
And at the very least, if B1 is one side in the double-sided diagram, shouldn't the map, the encoding map,
B is one side.
Capital B is
Capital
one
B is
CFT. Capital
One is
one
single
and
trace.
two are what? The two
One
sides
is single
of-
trace.
no,
Two is more than.
Oh wait 1 second. I had a nice picture about this.
Just
Yeah.
draw this because I get confused between one is one side and let me just draw it, please. I'm sorry to be so slow.
Okay, so here you have your B. Here you have your B bar degrees of freedom. It's all gravitons and like slight scalar fields. Okay, and then the way it maps to the CFT is as follows. You basically you have a highly entangled state for the bifurcate horizon. Okay, so which carries the entanglement of the area, and then you basically take these two guys, and there is a unitary which I can absorb in something, but this is the encoding unitary which puts it to the CFT.
So that part is fine. What is one, what is two, what is bars? Just
Okay, so good. So the point is, okay, let me. Thank you. Yes, I needed to do that. That's great. That's great.
B has parts B1 and B2.
Okay, so the point is, so this is capital B. Yeah. So the point is that this guy is going into B1, this guy is going to B2, this guy is going into B1 bar, this guy is going to B2 bar.
Okay, but then shouldn't the error correcting map be the isometric be from H physical, which is some bulk graviton, into capital HB or capital HB bar?
I'm thinking of it as mapping.
It's a product there. That confuses me.
No, because it's basically taking a state of the bulk, which is here. No, no.
The H code could be, are you using the state in the H code to be one sided or general?
I'm taking
some graviton lump excitation
Only
which
on
are
one side
imaging
or
on one side.
on one side, and then that would
Then that would be only on HB.
Yeah, if you
Chi B also, right?
yeah, if you take look, if you take it to be a one-sided state, a factor state, okay, then you can kind of partial trace out B bar and write a map from little b to capital B.
So Sandeep,
Okay,
let's say
but
you
here-
don't take any excitation whatsoever, right? Just the vacuum state. That's not a state in one side. That's not a state in both sides. So that's like the baseline integral. And now you actually have some excitement, and that will just go on this side.
Yeah.
That side. If you have
Yeah. Yeah.
Thank you.
Okay. Yeah, so maybe what I'll do now is I'll
Sorry, just one. So,
Huh?
is this for decoupling? Is it is one using the fact that this chi alpha is the same, no matter what the state in the course?
Yes.
yes, it's very important.
That's you're using that, yes. I mean, so depends on what you mean, but if you use that, then you can show decoupling. If you assume decoupling, then you can show this.
Oh, I guess that will just cancel in though.
Yeah.
So it has to be the same. Yeah.
Okay.
Thank you.
So maybe what I'll do for the from now on is I will try to like realize this in an explicit 2D CFT. Okay, well, sorry, that explicit is probably the wrong word to use. But okay, maybe one important thing to say here is this is about quantum error correcting codes. Okay, but typically the application to ADS CFT starts from here. Okay, because you can show that bulk relative entropy equals boundary relative entropy. Okay, and then you say okay, therefore ADS CFT, and you can show that ADS CFT is an error correcting code in a fairly trivial way, and therefore it's an error correcting code with the JLMS formula. Okay, which means that the subregion duality should be true and the RT formula should be true, and there should be some linear operator area which gives you the RT formula. Now there's something funny here, okay, which is that we know this thing assumes that you know the bulk dual of a boundary region. Okay, it doesn't allow you to, so it doesn't really give you the full RT formula. Okay, because RT formula says okay, you actually have to extremize the area and then minimize among all extremal surfaces. So you have to look for the bulk dual. So this is another way in which you have to input the bulk region into this story to actually get subregion duality and RT formula. Okay.
If I was doing it for the full CFT, not just one-sided CFT, then there would be no B bar.
In that case, I would be like, because we care about subregion duality. Do you want full duality? ADS CFT full, yeah. Then this is
No B bar, no alpha.
yeah, and then yeah.
Then it would be very simple.
Yeah, then it's like just
And then if you have an RT surface,
no, he's taking the full CFT.
no, but I mean, you could take. You don't want to take any subpart of
I was thinking first just the simplest case.
That's just a statement about existence of
Of a map.
Yeah,
And
exactly.
But then B2 would be, but there would still be a B2, which would be the high energy stuff.
Yeah, exactly.
And
Yeah, which would be in some way fairly trivial state.
So, well, I mean, there's not much to discuss, but
Yeah,
the simplest.
yeah, okay, good.
I mean, even in trivial, but I guess the non-trivial thing there is finding such a.
Yeah. Finding B1 and B2 is an exponentially complicated.
Derivation of ADS CFT, right? I mean,
Yeah, that would be a derivation of ADS CFT. That's right.
From this modern, sophisticated point of view, it's trivial.
No. See, it's trivial in the sense of there exists B1, B2, but constructing B1, B2 is deriving ADS CFT. Okay.
Yeah, just wanted to make sure. So here, the way you drew it, you are erasing B1 bar and B2 bar. Right?
Huh?
The part that you will be erasing would be B1 bar and B2 bar. Right?
Yeah, if you think about as an erasure code, information here is protected against erasure of B bar, yes, and information there is protected against erasure of that.
The way you do it, we are reconstructing on two parts of the both sides.
Yeah.
That's what happens.
Yeah, like the right exterior gets reconstructed on the right boundary and left on the left boundary. Yeah.
One last question. And
Right.
If it's too much, we can talk later. But I remember at some point I read this JLMS appendix that actually defined how you gave a proposal for how to define this one loop entropy. And there was a nice construction in which you kept some induced area fixed or something like that. Do you know that in your head? Can you
No, not off the top of my head. Like we can discuss this. Yeah.
with a
Yeah.
Yeah.
I don't think they could make it very,
Very precise.
Yeah.
I was wondering if that they had some sum over various things. And I was wondering if
That is in fact that, yeah. So because you keep the induced area fixed, this is different values of the area. Okay. In a black hole context, it's very easy. Okay, there's like you take a microcanonical TFD. Okay, the energy has order 1 by root g Newton fluctuations. Okay, and you can take split it into order 1 microcanonical windows, and each alpha is an order 1 microcanonical window. Oh, yeah.
But you emphasized that it wasn't quite energy, it was more like entanglement, right?
In the TFD case, the bulk boost energy is a renormalization. You can throw it away.
Okay.
But yeah, if you be a little more general, it's not exactly that.
So, Ronak, what would be the vacuum state?
The vacuum state,
Yeah.
there's no energy, there's no dynamics here.
There's no, so, no, but I mean so if you don't have any entanglement, which is of the bulk, I mean they will all serve. Basically, what I'm saying is that the vacuum state you would characterize by saying
A vacuum state, and what is
that the entanglement is just the entanglement of chi and no other thing.
is that right?
Because you don't have any bulk excitations.
But the bulk vacuum also has entanglement. Now, there's a question that I've been curious about, which is whether you can you can always set renormalize it so the bulk vacuum entanglement is 0, but I'm not sure if it's true. But bulk vacuum
The area term is in a sense the bulk vacuum entanglement.
no. Actually, this is there is a subtlety here because it's the leading part, but there's an order 1 part which is bulk vacuum entanglement, which you have to which can possibly be renormalized away, but I am not convinced there's a scheme that.
Suppose by vacuum I mean I just take the ADS vacuum.
There's some slight fields on it.
With some mass, I guess. Huh?
No, there's ADS vacuum, okay, with some light fields on it. So like,
Oh, but you have only one boundary.
yeah, there's one boundary, and yeah, the point is that if you
And of course I don't know what it is.
He's saying the actual wave function could be complicated.
But you're splitting into two parts. You're splitting.
I think you were splitting into 2 parts, right?
Okay, you're splitting into two parts. Okay.
That's why I'm talking
Then
about entanglement.
I
This,
thought the chi alpha part is
feel
the
like-
very short distance entanglement across one the area.
Yeah, so that's right. But that's right. The chi alpha part is like the area part, and then there is also some entanglement of the bulk vacuum.
Yeah, because of JL one loop.
Yeah, exactly, and that's the one loop
But
correction.
that was
And
your question, right? So
yeah.
that is what it is, right?
yeah.
No, yeah, I was interested in, I mean, I asked him basically, I mean, can we characterize the vacuum by just saying that the entanglement is just the area?
I am not convinced that there is a renormalization scheme of the point is that when you apply this to area CFT, there's a renormalization ambiguity in splitting it up, and I think there's a renormalization scheme for a given geometry and a given interval which will set it to be just area, but then for other intervals it might not be just area. I'm not convinced that one renormalization scheme always gives you just area.
Yeah, the bulk entropy will itself have several contributions. The leading divergence will probably be absorbed inside the normalization of the
You might have some leftover piece. So,
Exactly.
so suppose I consider multiple intervals, right? For this interval, I could absorb the entire thing into the area plus higher derivative corrections. Okay, but then I take a different interval. The question is whether the same scheme actually does the same thing for the other interval or not. I don't know that.
Even for different shapes of the boundary, you could get different
Yeah.
dependent contributions.
Yeah, that's what I'm thinking. Yeah,
No, but isn't all of that going in here?
yeah, but it's the point is that's not 0.
That's not 0 for the vacuum state.
We have for the vacuum state in general.
Can I say that the vacuum state then is the state of minimum entanglement?
No,
Minimum entanglement trophy?
no.
So in fact, the minimum entanglement is very high energy state.
Yeah.
I could just break all the
Yeah, exactly. Yeah,
some UV state.
No. Basically, I wanted to just get that.
that's
Is there
very
a
that's.
state where you just have
Just
that?
get
I don't believe so. No.
Firewall kind of thing. If you disentangle the two sides from the buffer,
No. I didn't want to decide. I just
No.
wanted that contribution.
I think you can't. You really can't get just that. The area is never the full answer, unless you fine tune like a lot. Like you can but typically no.
I mean, at least this formula is saying if you don't have entanglement in the small baby bar degrees of freedom.
But this formula is not. That's what I'm saying. This formula is not about ADS CFT. It's about general QACCs in finite dimensional case.
Maybe that's what you will now make
Yeah, that's what, yeah. So even when I will take the simplest possible case and try to apply this in that case, and we'll find like interesting subtleties. Okay, so let's do that. Let's take a 2D CFT and actually create a code.
And the JLMS description will give us a probability for having a certain area.
Yeah. Like P alpha is like the probability of an area, like yeah. Explicit construction in 2D CFT. Okay, so this is okay. So let's consider a particular. We'll consider HCFT. So tensor 2, which means you have two circles. This will be B. This will be B bar. Okay. So now I have to pick a code. So I will pick a code. Here I kept H code to be outside HFizz. Okay, so HFizz is HCFT tensor 2.
You're looking at thermophile double of.
No, not yet. That's a Hilbert space.
Okay, but why do we have two?
I decided.
Okay, you want to take two copies of this.
Yeah. My Hilbert space is HFizz is HCFT tensor 2. Okay. So I'm going to here I kept H code outside of HFizz, okay, which is useful for some cases, but I'll actually think of H code as just the image of H code in HFizz. So I'll think of H code in HFizz.
H capital B1. H capital B1.
H capital B1 B1 bar.
Sorry, capital B1 B1.
And actually it's the chi alpha just
Are we in some large N context?
no, not yet.
What is H code then? Just the
I'm going to define it. Yeah. I will tell you where we put large C in. Like there is a particular step where large C becomes important. Before that it is not important. Okay. So H code is defined in the following way. You define epsilon to be the thermophile double. So every equation I write will be up to a normalization because for obvious reasons. So epsilon is the thermophile double of some temperature epsilon, which is small.
H code is a subset of this?
Yeah, you're right. It's a subset.
Now you have epsilon and you have E on that side, and just to make sure, what is oh, so you're not weighting. It's not a thermophile double. Which would have been
E semi.
Oh, sorry. You're right. I mean, I messed it up. Epsilon is the temperature. Yeah. Okay. Yeah. And now I will consider H code to be the following Hilbert space.
So you do not in mind that epsilon is small?
Yeah, epsilon is small. Yeah, and if you set the radius to be 1, epsilon is much less than 1. Yeah, it's like a high temperature state. Ideally, I would like to take the infinite temperature state, but normalizability.
Trying to find like a zero length form.
Basically, yeah. So I'll take the code subspace is given by arbitrary functions of the left trash tensor acting on this infinite temperature thermophile double state. Okay. So examples of this are basically you can consider any thermophile double.
TL is the left stress tensor, TL bar is the right.
No, TL bar is this is a 2D CFT. 2D CFT, TT bar.
Oh, TT.
That's the word. Yes, thank you. I was losing the word.
I'm just trying to make sure all the
Yeah.
bars. Okay.
Yeah, good. So this is a completely different bar.
So this left right is now what you call DB bar?
Yes, that's right. Yeah, okay. From now on, B equals L, B bar equals R. Okay.
Then why is H code defined only on the left?
It allows me to not worry about some subtleties. Like if I allowed for right operators, then you could create weird entanglement structures, which I don't want to deal with.
But here all this dealt with all that only, right? The entangled state in the H code.
No, there's still, you're starting off with a highly entangled state. You can anneal some of the entanglement away, but you can't the idea is that you can't create weird new entanglement.
So as far as L0 is, so if I think of the stress tensors in terms of the Virasoro
Yeah.
then as far as L0 is concerned, I don't ever have to act with L0
On the right.
Right, because L0R will generate the full subspace.
Yeah.
Right?
That's the idea.
State is special.
Yeah.
But isn't that also true of the higher Virasoro generators?
That is basically also you can always do you can actually kind of do a CJ map and like
This is the full thing.
yeah exactly. I'm just yeah. Otherwise you'll have like entangled descendants which you can act with entangled descendant operators which confuse me. This is a linearly closed subspace.
Yeah.
Okay, it has some. Let me just tell you what the set of some things it has.
So wait, just to understand Unkar's comment, you're saying that you're saying that if I put I left times F on the other side, that is the same thing.
Yeah, basically
F on both sides.
basically TR
But he keeps saying that
is effective.
it's a new entangled something.
So TR is basically this. Okay, acting on this state, it will just this part. So you have a highly entangled thermophile double. What this does is it so this is left, this is right. It erases this much, which is E to epsilon h, puts a T, and then puts it back. Okay, you can always do stuff like this to put it on the other side. But like yeah.
And just to, if you put both FTL and FR, is that different or the same?
I feel like it should be the same, but I got confused while trying to prove it. So I just simplified my life by saying this is my H code.
But Omkar, I can understand your argument for L0, but for L1 etc. you have raising on one side, no?
Yeah.
So that's different.
But yeah, you have to then say a little bit about.
Yeah, you have to. This
In
is
order to
see. This
have
is why I.
other side, you need the
This is why I didn't put the other one. It gets confusing. Yeah. Holomorphic, anti-holomorphic.
stress tensor.
I thought L was B and R was.
Yeah. No, this bar is this bar is complex conjugation, not complementary. Yeah. Okay. Yes, I did not notice this clash of notations while thinking through the stuff. I'm sorry.
Right, so actually that brings up one question, right? Because there are degeneracies in the spectrum.
I will assume a generic CFT without degeneracy just for simplicity. You're right, but I think everything I say can be trashed for degeneracy.
Because then you have to say a little bit about.
Little bit, yeah, not much, but yeah, you have to, yeah.
You're saying using the primary spectrum?
No, in the descendants.
Oh no, sorry, yeah, sorry.
In the descendants,
Yeah, what are you worried about degeneracy in descendants?
don't you have to say a little bit about which state here is entangled with that, which state there?
Here I'm assuming that, okay, you have to, I would say that you start with the primary and then like map this corresponding descendants, yeah.
Okay, in that case, I think what I said is correct, right? That
Yeah.
You can take L1 and map it to an L.
Yeah. Yeah, the degeneracy normal descendants are important. You should be, I cannot assume them away.
Okay, so if you make that choice, then I think this is the
Yeah,
full
yeah.
subspace.
Yeah, I have to for every Virasoro module, I will at some point have to define a particular, what do you call it, orthonormal basis, and then using that orthonormal basis, you can do anything you want. Yeah.
But this product is module product.
Model.
Module product.
Right now, it's not a it.
By E you mean the sum of E's, right? Sum of E's in a given module and sum of E's in a given module.
No, this is state by state. This is state by state.
Oh, but then degenerate, no? In the second level, whether L minus 2 is entangled with L minus 1, L minus 1 or same descendants?
No, yeah, I'll basically choose an orthonormal basis for each level.
And then the same basis on both sides.
Yeah. Okay. Yes. Good. I didn't expect anyone to catch that particular certificate. Okay. Cool. So I have just defined the H code. Okay. And yet again, like I am I am just defining it. It is closed under linear superposition. So therefore, it's a Hilbert space, and that's all I really need to justify it. Okay. Cool. So what are some things it contains? So for example, you can consider f equals e to the minus beta minus epsilon L0 plus L0 bar.
So just about the previous discussion, if I define the state through a Euclidean path integral, then it's clear that acting with this operator here can be proved.
Yeah, that's exactly that's all I'm saying. That's what this thing was all
And
about.
that would be for, but I'm saying that's then for all descendants.
Yeah, that's right. Cool. So
Probably that's the only state for which you can. So
Huh?
that's how you want it entangled, right? Defining.
yeah, that's right. Okay, so you can consider this, and then the state you get is like just half, I guess.
So what is this? Half beta minus
Epsilon. So you just get the TFD. Similarly, you can take you can take a time evolved TFD. Okay, any time evolved TFD in the state. Similarly, you can take TFD with random descendant excitations on both sides. All of these are in the code subspace. Okay, so this is my code subspace. So now let us actually try to
just to make sure, sorry, that is rho, that's the
F. Yeah,
Time evolved, you mean Lorentzian time evolved,
Lorentzian time evolved, yes.
but Euclidean also.
The Euclidean would just change the temperature, right?
Yeah.
just to make sure, so this is an operator
I'm saying that
acting on the left side.
acting on this epsilon.
But it's part of, oh, is that F? Okay.
Yeah. Yeah, you can take you can consider TFDs, time over TFDs, TFDs with random descendant excitations, all of these we know the bulk duals, like it's a two-sided black hole with some time evolution. There's actually a paper by Gautam and others which explicitly work out the bulk dual for TFDs with descendant excitations. Okay, all of that is fine. Okay. Oh, one important thing is that descendants the dual is boundary gravitons. Okay. What this means is that basically, if you have some descendant acting here, when you fill in ADS, it looks the boundary looks a little bit wiggly at finite cutoff.
Yes, your code subspace, I thought translating from it here was you make your Euclidean path integral and then act with contours of the stress tensor any number of times.
Yeah.
Okay, fine.
Yeah. I'm just kind of giving you examples of what is in the.
Then you move it to the other side.
Yeah.
Because it's just a
Yeah.
contour.
Yeah. And if you hit anything in between, then we know the Virasoro algebra. One can just solve the Virasoro algebra to pass it through.
And naively from the bulk point of view, you might have thought that there are two boundary gravitons, but there are not because of
There are two sets of boundary gravitons. There's boundary gravitons on the left and the right.
But you just discussed here that there is
No, I can do this, put a boundary graviton, do this, right? So I can put a boundary graviton on the right also.
Isn't it true that on each set of states, L acting on one side can be related to L acting on the other side?
That is true.
Okay, so then there's only one. Within this subspace, there's only one set of boundary gravitons.
But I mean, the point is you can have different boundary gravitons on both sides, which are just L's here times L's here. Yeah, but
Yeah, I was just saying that there's some gravitational constraint.
the gravitational constraint I will work out. It does not affect the boundary gravitons actually.
No, but I mean, I thought that if you had a boundary graviton here, it was created by this.
Yeah.
So I can move it there
Yeah.
and rewrite it as a boundary graviton.
Yeah, that's true. That's just a change of coordinates.
Change of coordinates.
Like you basically have two wiggly boundaries. You can always straighten one boundary and then follow the Schwarzschild coordinate. It becomes more wiggly on the other side. Yeah.
So that's why I was saying the phase space only seems like it has one.
Oh, is that right? Perhaps I have to think about this.
But it's clear from this point of view, right? Because the same state is either this or that.
I see. Okay, I would have to think about this point. I hadn't.
Besides, from the Euclidean path integrals, isn't it just a...
No, I agree, but I'm confused about. It looks like I can put different boundary gravitons. Of course, you're saying there are relationships between these different states, but.
Well, I can just make it by acting with this T thing.
Yeah.
And now I move that.
But what if the operator?
But I'm just saying that. So.
If it is a local operator.
But
then
I thought that,
So, see, let me just.
not topological, not local operators.
right.
I thought all operators he was considering were.
But L is the other Fourier modes of local things.
Yeah.
So I can write any local T in terms of Fourier.
No, but it's certainly true that T inserted here is not same as T inserted here.
No, I think the point here is exact that we are mixing up Euclidean and Lorentzian. In the space of Lorentzian states, T left and T right are different operators, but it's true that T left can be written as a Euclidean evolution times T right times Euclidean evolution. Okay. Yeah.
You're saying that maybe they're time-dependent kind of code.
Yeah, basically, effectively, yeah. There are some the coefficients become state dependent. So, it's not like a linear operator that annihilates all states. It's a nonlinear operator that annihilates states because yeah. Otherwise, a KMS condition would tell you that two different systems have the same algebra. Yeah.
So just if I just quantize ADS3 gravity around B, like B0, then I'm going to get two sets of
I believe so, yes. Yeah.
the gravitational constraints don't get.
Yeah, the gravitational constraints will only affect the primary part. Yeah.
Yeah, like in 2D when we talk about Schwarzschild, we think there's only one Schwarzschild allowance in 2D.
No, it's actually two Schwarzschild with a coupled zero mode. This is a yeah, but this is anyway. There's a very nice paper by something Chua and Yikun Jiang, which explains this very in 3D gravity. I mean, it's also there implicitly in various 2D papers, but the Chua Jiang paper is the best written one.
Yeah, sorry, from correcting what I was saying, I think it's because these LNs are not conserved in time evolution. This L0 doesn't come
Yeah. So yeah, they become state dependent coefficients. Yeah.
Only the 1 and -1. No,
Only 0.
Yes.
Yeah. Cool. And yeah, the L0 constraint is there. Right? Like the yeah.
So sorry. So then in that case, acting on the LNs
Mhm.
on one side and acting
No,
on the other side are different.
They're different operators, but it's that TR can be written like this. But the point is these coefficients, right? They're state dependent. Okay. So it's not like TR minus this is not like some nice linear function thing killing your every state. Okay. If I act on beta, then you have to put beta here and so on. Okay. Whereas L0, it's not state dependent. It's really just L0 there is equal to L0.
Oh, okay.
Yeah.
Okay, that.
Well, not L0, but a particular Casimir that I will write down. Good. Okay. So these are the sorts of things we have in our code subspace. So now let me just we will create the sort of block diagonal decomposition of Harlow by studying the wave functions. Okay. So the Hilbert space of HCFT we all know looks like sum over primaries, left moving tensor, right moving Verma module of the primary. Okay. Good. And I will take a generic irrational CFT so that there is no there are no degeneracies among the primaries.
Just confirm this operator which takes left to right, you say it's state dependent because of epsilon, right?
Yeah, basically these things will give you coefficients which
But
depend on.
it's the same map for the full chord subspace.
No, it's not the full same map because if I start with beta, then I put beta here. Okay.
No, I mean for the full chord subspace, the same mapping works, right?
No.
TL on the right.
No, TL on the right is related to TR on the left. So TL and TR are related by some conjugation, but that conjugation is really just density matrix of whatever state you care about.
I can't write this for that.
No, yeah, because just imagine this was beta, right? Like if you acted with a beta thermophile double, this would like take you only this epsilon would just take you a little bit down, won't take it all the way to the other side. So cool. So your HCFT always looks like this. This is a well-known fact. That's right. Written in fancy QI language, as Shiraz would say. Okay.
Sorry, I mean, so this is for each individual CFT,
Yes.
and just explain what.
So it's a sum over primaries. For each primary, there's a left moving module and a right moving module, right? It's just this. Okay. So and then we can consider a basis which is just okay. For the rest of this talk, I will ignore everything right moving. Okay, pretend because it just adds notation, won't change any of the physics. Okay. There's a basis of states like this. Okay, you just act with some descendant of a primary and evolve to your circle, right? And I've assumed that I've picked a orthonormal basis for my Hilbert space, for my module space. Okay, the specific orthonormal basis will not matter. Okay, so generic ICFT basis the
I mean ICFT.
irrational.
Irrational.
Yeah. And the third important fact, which is the least well known, is that there exists a Virasoro Casimir CL naught, so that CL naught on L minus n 0 gives you h of O. That's O, sorry, not 0. It just measures the primary dimension. Okay, this is I forgot. I have not. I don't remember the reference for this, but a version of this was written down by Fuchs in like the very early days of CFT.
Acting on a general descendant state,
Gives you the
some primary. It gives you the primary dimension.
yeah. You can just think of it as it kind of undoes the descendant, like it acts with lowering operators, then acts with L0, then acts with raising operators to come back. Right? Cool. So this is my thing. So now I will just take one of these states, okay, and decompose it in that basis. Okay. What do I want to? So basically, we want to consider L minus n O, L minus n prime O prime on some.
How is it tangential? But do you know how this Casimir look like?
You have to use the inverse of the gram matrix.
So it's very complicated.
Yeah, there's a recursion relation and so on, but like it's the existence can be proven. If you pick a particular orthonormal basis, it's much easier to write down. Well, it's less complicated to write down if you write down take a particular orthonormal basis, but it's a different sort of complication. But yeah. Oh yeah, no. For me, at least emotionally, the fact that I could write it could be written in terms of L's.
Part of the universal enveloping algebra, no?
Yeah.
Casimir, meaning it's made from
Yeah.
L's.
Yeah. It's in fact yeah. So
The existence. I don't know whether you use it.
I will use it.
It's an element of universal enveloping.
No, I don't really use it, but it's important for me. It's emotionally important for me.
Okay.
Okay. I was like, okay, this is explicit, whatever it is. Okay, like you can open that paper and like read about it in terms of the inverse gram matrix, which they call the Chopin law from or something like that. Anyway, so you basically want to calculate a wave function of this sort. Okay, which is so every state like this in your H code kind of looks like this. Okay, with some stress tensor excitations. Okay, and now you just put those guys. Right. So now you have this is a sphere, okay, conformally speaking, and it's a sphere with just two primary insertions O and O prime. So this is proportional to delta of O prime. Okay.
Just 1 minute. One of those is a state in
The
R and the other is in L. Is that what you're doing?
yeah. So this is R is L.
Okay, so those two are in R and L. Right?
Yeah.
Those L
Yeah. Let me exactly. Let me put this in L and this. And yeah.
Okay, good. Thank you.
Okay.
So O are the basis
O is the primaries.
primaries.
Yeah. Okay. So what this means is that HCFT tensor 2 is equal to plus over O prime.
Psi is a cold subspace state here, I imagine.
Yes. Thank you. Psi in
No, it's okay.
yeah. V O prime R. So yeah, two CFTs can be written like this. Again, I am pretending it's a chiral CFT for simplicity. But H code is okay. So now, what do you say? So you can again see that these O's are like alphas. Like the alpha on the left and right need not match for a general state, but for a cold state they do match. Huh?
Had you enlarged your definition of code subspace to include operator insertions in the Euclidean thing, then this diagonal thing would have broken.
Yes. In fact, if I like allow light operators, then I would have to use ETH to relate things. Yeah. Only stress tensor. So that's why it's delta O prime. He's saying, suppose I took a different code. Okay.
No, but your code subspace, your right hand guy was, I think.
So
code was more restricted than this, right? So what is this notation again? The new 0L is a descendant.
this is the space of descendants.
And,
So Verma modules.
but aren't you taking descendants? You're taking the state epsilon and taking descendants on one side only.
But again, you can create descendants on both sides.
But I thought, is that clear that therefore you're saying the code subspace is bigger actually? It's descendants of one side, tensor product sort of the same descendant on the other. That's what it is.
Descendants of the same primary on other.
Of the same. I mean, if you had.
It could be different descendants, but same primary.
Is that what the full code subspace is then?
Yeah.
But you were not allowing any primary
So-
action on the code subspace. You just
No,
said
no,
the
but-
code subspace is constructed by the action of V.
But the original state we started with had all primaries in it.
Because it's a thermophiles.
Yeah, it's all primary.
Yeah.
But
So
now, yeah.
His point is the thermophile double automatically is O with O.
yeah,
Oh, we go.
yeah, and
including descendants.
yeah, exactly.
And
Yeah.
all descendants, but the same descendants on both sides.
Same primary, different any
Because
descendants.
You're allowing some insertions. The thermophile double may have had the same descendants on both sides, but now you're allowing 3 insertions, which will mark that.
Yeah,
But you allow descendants on both sides.
yeah, effectively. Yeah.
The thermophile double would. Oh, you mean in your insertion? That he was not very clear.
Yeah, no, you can because you can always a descendant here is always related to some descendant here in a state dependent manner. But you create one state, that's fine. You can create whatever state you want by acting here. I did not say that the operator acting on the left was unitary. If it was unitary, then you couldn't push it to the other side. But for non-unitaries, you are like allowed. You know?
Sorry, what is the last duality?
Huh?
I'm not getting what is the point that you're making here.
No, what I'm making, the point is that the wave function is supported on the left and right primaries being the same. Okay. Therefore, whereas the general state in 2 CFTs does not have this left and right primary is the same. So the code subspace is a subspace of the full CFT where the 2 primaries are the same. So these O's are exactly like the alphas of Harlow.
Ah, okay, yeah.
Yeah.
Yeah, that's okay. I see. Okay.
So this is very explicit. Someone had a question. Yeah. Okay. By the way, I should just say that this code subspace is inspired by a work of Cassini, Huerta. Let me see if I get everyone. Magan, Pontello, which was a really, really inspiring paper for me, but it took me 5 years to do something with it. But yeah, yeah.
The O's are not exactly, I mean, for instance, the O's could have microstate operators as well, right? O's are all primaries with like,
Yeah, O's are all primaries.
so in what sense should I think of it as like a bulk supersymmetric?
Yeah, it's not. In fact, I will get into that. Yeah. But right now, I'm just starting the CFT. I'm like, okay, I'm following my nose.
If the O's are like alpha, what are the B's?
We'll get there. Yeah. Okay.
Where did you use that? It's a chiral CFT.
I did. It's not really a chiral CFT. I'm just dropping the V bars simply because they do exactly what the V's do. It's just I could say that V now means V tensor V bar. Nothing changes. L minus n means L minus n, L minus n bar. Yeah.
In
Yeah.
particular, if you're non-chiral CFT, you were looking at the diagonal invariant. You would, your code subspace would be O bar, O bar.
Yeah.
Some O.
Yeah. Well, O is one operator, HO bar. Anyway, whatever. Okay. So the point is that now we see that the O's kind of act like alphas in the sense that here is an operator, so here is an index that would not be the same for the left and right, but in the code is. Okay. So good.
Yeah, but as Shankar was saying that it's kind of formally like alpha only.
Yeah, I know. And that's like going to be like the fun part of the talk, making it more less formally like alpha. Yeah. Yeah, no, it's true. In fact, like I'm going to like drill down and say why it's not like alpha. Okay. The reason it's not like alpha. So what we have then is that every state psi can be written as sum over primaries square root PO psi O. Okay. And notice the lack of a chi O.
But as you were saying, Ronak, I code subspace has this alpha sum, then the image vector space automatically has some sort of alpha decomposition.
Yeah,
right?
yeah.
So you are just making it so that it matches with O.
Yeah, what I'm doing is I'm, what is it? There we picked a code subspace and then an isometry. Here I'm just picking a particularly nice subspace. So I'm kind of looking at VH code. I'm not defining H code separately. Okay,
Yes.
VH code is defined in a natural way in terms of like all thermophile doubles and all.
Yeah.
And I'm like just staring at VH code and seeing that it has a structure.
Right, but I'm saying even if you had not defined this code subspace in this careful way, so that the operate primaries are not changing and so on, finally it will, by definition, you will construct some alphas in which the physical Hilbert space will be decomposed, right?
I'm sure if you take a different code subspace, you'll get different decompositions.
Yeah, decomposition. It just will not match with O.
Yeah, sure. Yeah.
It was just a nice choice that it matches with.
Yeah, this was like the first thing. My real interest was actually including some light operators and thinking about the decomposition in terms of ETH and so on, but I haven't got there yet. Okay.
So this is Hilbert space 1 CFT.
Of 2 CFTs.
What is SIO?
So SIO is in VO bio, VO left, VO right. It's some state.
This is a state inside your code subspace.
Yeah. Every state looks like this, and notice there's no chi-Os. Okay, which is a version of Onka's observation that there's no reason to believe that these have anything to do with bulk degrees of freedom. Okay. Now, and there's actually a good reason there's no chi-O. Okay. What is chi-O? Chi-O is the degrees of freedom that you can't touch. It's like, or another way to think about it is that it's in each O sector it would be some entanglement that you cannot get rid of, right? Because you can't touch it and it has some minimal amount of entanglement in the O sector. But the point is that my code is too big, because you can always consider the following state: H code d2 e to the minus beta plus it h left h left. I'm messing up my Fourier transforms. One second. E to the minus it h left minus e naught. Yes, minus some e naught acting on some beta will give me something proportional to e naught, some factorized state, okay, which will be in one of these modules, right? So the point is that in each module I can create a state with 0 entanglement, okay, which means that there is no irreducible entanglement within a module.
Minus I tau, what is between the bracket?
HL.
HL minus E.
Yeah. I hope I did the Fourier transform right. This is supposed to be a Fourier transform that lands you on a particular state. Okay, minus infinity to infinity.
Within the module, there is some order 1 operator.
Right now, I'm not even doing that. Right, I'm projecting on a specific energy.
Specific state.
Yeah.
You're just saying that this thing that you had, O module, you could choose one state and one state. Right?
Yeah, and that is in the code subspace,
Yeah.
and therefore there is no chi-O part, which is the chi-O would be some irreducible entanglement within each module, but there is no irreducible entanglement.
We could have chosen primary times primary.
Yeah.
Plus.
Over. Exactly. So the point is that this code is very stupid. Okay, which is why there are no which is why there is no area operator, or rather the information theoretic area operator is 0. Okay.
But can you, okay, so I mean, the way I'm understanding is that you start with a thermophile double state, and you say that the code is where you just act with the T's on one side, and then you observe that it does not change OO,
Yeah.
and then now you are writing this.
Yeah.
Now it's true that it's the same OO, but can you make that with the thermophile double with the TT, with the T action? This is the one, sorry.
This is here you have it. You can just take it to be epsilon. This is literally the function of HL.
Projecting on a state with one energy.
Yeah.
But you don't want to make, I mean, you want some, okay, fine.
No, I'm saying like this, the way I define my code, see, I'm being rigorous, right?
Yeah.
I defined a code. What state does it have? It has this state.
Yeah, fine.
Okay. Now the point is rigor can be idiotic. This is me choosing an idiotic code. What?
Are you assuming this?
Yes, I'm assuming that there is no primary degeneracies. Which yeah. I mean, you can deal with primary degeneracies, nothing much changes, but like it's just more notation.
I just said because you said there's no irreducible entanglement, and if you're only using the 8s, then there is entanglement because of that.
Sure, that would be some order 1 thing. Like typically you might have like 5 primaries together or something, and you get a log 5. Okay, which is not super important. Like our area is going to have a 1 over G Newton in front of it, right? Yeah. Good. The point is, yeah. So this code does not have so.
It's a little like Subrat. Subrat has this AD and Hamiltonian, and then with that he can do many things. So you have the Hamiltonian.
Yeah, I mean, yeah, exactly. I'm doing much less than Suraj even.
No, but I'm saying the fact that you have the Hamiltonian allowed you to.
Yeah, exactly.
And it's like in my area 0.
Oh, basically because the general state. So, what was the role of that chi alpha? Right? It said that if you pick a particular alpha sector, there is a minimum amount of entanglement that you can have in that alpha sector, which is the entanglement of chi alpha. Yeah. Okay. Now, here is a state for any given O. I can construct basically OO. Okay, by taking this to be E of O. Okay. And now in this O sector, there is a state with 0 entanglement, right? So the corresponding chi has 0 entanglement, which means it's not there. Like a 0 entanglement state, like yeah, it's a two one-dimensional Hilbert spaces. Who cares? So the point is the A information theoretic is 0 in this case.
Maybe a naive question, but for you to expect a non-zero area operator, would you want a very large E there? Or?
I will tell you I will tell you metric to get a non-zero area operator.
What was this A information theoretic? It was the part coming from your chi,
So yeah,
which you didn't have.
yeah, yeah.
Yes.
It's a 0 operator.
I was trying to talk about the comment you made earlier about there being like order 1 number of operators. Wouldn't that increase when you take appreciable like E to be an appreciably large number?
See, yeah, but if you take a generic irrational CFT, you don't expect like order 1 by G Newton amounts of degeneracies in the primary, right?
The dimension is very high.
Even if the dimension is very high, you expect exponentially small spacings. There's level repulsion.
So this is happening because your the size of the code subspace is so large that you cannot actually take V to be less than a one side. That's why we are getting.
No, it's not that quite, but because clearly the code subspace is a subspace. Okay, it's just that it contains factorized states. Okay, so there is no irreducible entanglement anywhere. Okay.
All entanglement is bulk entanglement.
Yeah. Okay, I like that slogan. I'll put it somewhere. Okay, but okay, sorry. Actually, one of the points I'm going to make is that H code is not H bulk. So let me get there. Okay, so now. What are there 2 options to get an area operator? Okay, one is to be a little more clever about my code subspace, but I am lazy, so I won't do that. The other is I will do a coarse graining. Okay, and the real reason I am choosing to go the coarse graining way is that I think coarse graining is going to be important in general. Okay, and the technical statement is that we are going from exact QAC to approximate QAC. Okay, and approximate QAC is better in holography. Okay, which is why that's why I want to keep focus on the coarse graining part. Okay, so what I will do is how the way coarse grain is, I will bin primaries. I will construct a bunch of bins and put different primaries into different bins. Okay, so how do I do that? So you have energy, you have a bunch of primaries. Okay, imagine there are random spacings. Okay, so one possible thing is I could just say, okay, here is a bin, here is another bin, here is another bin, whatever. Okay, but this is sort of not smooth. Okay, and it's sort of a bit sad. Okay, so I won't do this. So what I will do is I will construct a bunch of functions which I call f alpha of O. Okay, alpha will be a contiguous set. Okay. Yeah, f alpha of O. So you have a bunch of functions. Now, and I will demand that if I fix O and integrate over alpha, I get 1. Okay, so this is called a partition of unity. Okay,
Sorry, can you say that a partition of?
unity, because I am partitioning unity at every point. Okay, so now
O is the center of your thing.
O is no, it's like is a function. It's a alpha is like the center. O is like the actual x-axis.
The argument.
Yeah, which is why f alpha of O. Okay.
Sum over all.
Yeah.
This statement is like if you choose any primary and you integrate over all the functions that you have it.
You get 1. Okay. Another way to think about this is you give me a primary O. Okay. I can there are many bins on that primary. I put it in the alpha bin with probability f alpha of O. So f alpha of O is a conditional probability. P of alpha given O. Okay.
Alpha is like the bin index.
Yeah, alpha is the bin index. So
O is the center.
no, O is the actual primary.
Is the where you are. Where you are.
Yeah. Okay. So and this is a conditional probability. Okay. In particular, there is if I give you a conditional probability, P alpha of O, I can consider a joint probability, which is your probability of O, okay, which is whatever that is, times P of alpha given O. Okay.
So, this is quite different from the way we do this. I mean, we would understand this reconstruction, etc. in ACF, right? Where the code subspace will be made out of single trace primary.
This is very different, yes. The
The reason you kind of go towards this picture rather than the conventional one is because you have nice alpha division there.
that one, like it's a good code. It's like it's an elegant code. That's the original reason. But also, I think that what I am doing here will be required even in the more conventional case. Okay, and I'm just taking a very simple case to start understanding
Yeah,
it.
that's what I would then question. I mean, okay, we will see, but I don't know why won't that conventional picture to have any of these complications? I mean, there is no O, there is no.
No, their AIT, the information synthetic area will not be 0,
Yeah.
but I still want to do something like this, and I will explain why later.
Yeah.
Okay, it's like popping up. Okay.
When you say f alpha of O, you mean f alpha of H of O. That O is a number, right? The dimension of the primary.
Sure, you can make it a dimension. I can also just think of it as a space. Yeah, like if you whatever you want, it doesn't make a difference. Yeah.
Morally, you're going to get like a degeneracy at E, which is like the Gardi formula, right?
Huh?
Morally, you're going to say that this binning lets you say that there are
It's good.
a number of.
Yeah, basically that's where I'm going.
And what do you mean by P of O? Is it like
PO is the probability of finding the O sector here.
When you've drawn that f alpha, there you're thinking of that O as being H of O, right?
Yeah, I am being very I'm equivocating between O being a number and an operator. And like yeah, because literally it's just like a index. It like doesn't matter. Yeah. Yeah. It's really 2 copies of the real line because there's H and H bar, but I'm forgetting about H bar.
So I don't use notation. The
Mhm.
capital psi you wrote at the top, which is summation over PO psi O. The psi O is defined how some left
Descendants times right descendants.
times
It
right.
could be some entangled state of left and right descendants also.
But the same descendant, right?
No,
From left
could be
to
different
right.
descendants.
You're using that. Okay.
Yeah.
Anything.
Yeah.
Of the same primary.
Yeah.
Left and right is terrible terminology.
Thank you.
Yeah.
If you think of left and right,
That's
CFA.
Yeah, I know. And like the other option was B and B bar, where the bar was not holomorphic, anti-holomorphic. So, yeah, yeah.
But just to
It's,
understand,
there, nothing is inside. There are 2 different sides.
but just to understand, it's a code subspace because it's the same same primary on both sides.
Yeah,
I'm just making sure.
yeah.
And now he's going to somehow further restrict, I think.
Yeah, so good. I'm going to course grain. Okay, and I'm going to get non-linear. Anyway, I am going to get some non-linear relationships. Okay. So now the fun fact is I have P alpha of O, P of alpha O, joint probability distribution, and when I have a joint probability distribution, so let me define H of O as minus sum over P O log P O. Okay. So see F alpha of O. What is F alpha of O? You give me a primary O, I will put it into the alpha bin with probability F alpha of O. Okay. Another way to say this is that F alpha of O is a conditional probability. Given O, it is the probability of alpha.
Given O, it's the probability of alpha.
Right, because that is my algorithm. It's a conditional probability. Okay. Now I have a original probability and a conditional probability that gives me a joint probability.
What was PO?
PO is just the thing in the state. Yeah, it's the original. Yeah. So for every state, there's a joint probability now.
So now your code will not be diagonal because of this mirroring.
And let me get there.
In what sense is it coarse grading?
Huh?
In what sense are we doing coarse grading here?
The bins have width.
So at which stage are you going to do integration?
Huh?
At which stage do you have to will you do?
You just grade O with that.
Yeah, I'm trying to trade O for alpha. So like I'm trying to trade a fine grain index which is O for a coarse grain index which is a bin number.
PO is the probability you have O, and then of the times that you have O, P alpha O is the fraction of those that come from the state alpha.
Yeah. For come from the bin alpha. Yeah. It is the probability of having O in the original state.
Oh,
I will maybe I'll put this in pink to.
And O stands for any state.
O stands for primary. O stands for a primary.
When did you say that? I thought you
Because
with some over
because the
probability
structure of the
states.
code, no structure of the code. So is that it's like there's a different state for every primary. It's an arbitrary state for every primary. But any
Oh, psi O is some arbitrary state built on that primary.
Yeah.
That's right.
yeah
And PO is the amplitude to be in that state. Right?
in the primary
So you
in the primary Hilbert space.
it's O times O. O on the left and O on the right, though not O and holomorphic at all.
I see. So psi O can be general states.
It's some general state in the two modules.
Now he's forgetting about the module part of it. Just
Yeah, basically.
Which,
yeah.
which prime?
Yeah.
So you're getting about the module part, but the whole code subspace includes.
Yeah, but I am only.
This code thing somehow.
Yeah, just yeah. What are you saying?
Now with the thermophile double state, sir, this is a bit of an.
For a thermophile double state, this is like this is effectively e to the minus
No,
beta.
In that case, what is the pairing? Is the module by module or state by state pairing?
In thermophile double, it's also state by state. But in general code states, it's only module by module.
This is a different code subspace now.
It's the same code subspace. It's the same code subspace.
You're going to do something more now.
This is the same code subspace where you have the same module on both sides, but arbitrary states within the module on each side.
Yes. And here.
That is what this is, right?
That's what this is.
Because you have on the two sides you have new VOL and VOR. Okay, it's some state within those two modules, but the point is it's the same module on both sides, so there's only a single probability for the primary.
And then your beta epsilon over 2 factor, which depends on the descendant, is incorporated in.
Like all of that stuff. Like this F will make arbitrary descendant things.
Only the primary dimension from the beta epsilon, not beta, from the epsilon L0 part comes in PC.
Yeah, but in general also you can like do something else. You can have like a different thermophile double. Which yeah,
You define, so it's a more general code subspace or something.
it's the same code subspace I had before.
You started with something special.
Yeah, I arbitrary function on the left stress tensor acting on a high temperature thermophile double.
Yeah.
Right? So I'm just then I argued
Some particular P zeros, right? Because
in the epsilon state. But then the point is that the left stress tensor can change the POs.
yes.
Okay. In particular,
Okay.
yeah.
It changes how the descendants and so on.
It changes the probability of each primary also, because you know the e to the minus beta h, okay, can make high energy primaries more less and less.
Let's say you weight it with the energy of the primary.
Yeah, exactly.
That changes the.
Yeah, exactly.
I have to see the epsilon states have a definite weight, right?
Yeah, but the
Yeah,
f
that's with
part.
an operator plus. Let's say you act with L0 on this.
Okay.
So then L0 acts differently on each state.
That's differently on each state.
So it changes the effective.
Yeah,
The relative weight.
Those are included.
yeah.
Okay.
Like you can get thermofield levels of arbitrary temperature, right? So they clearly have different weightings on each primary.
The reason you got factorized states was you let the temperature go off to
No, because actually I did a Fourier transform to make factorized states, but
time could run to infinity
yeah, exactly. So
as large as C or something.
yeah, literally infinity, because I want it to be enclosed under linear superposition. Okay, see, yeah, this is one important thing, by the way, like which a lot of people have trouble with this, because what I'm doing is I'm taking finite but large C, fixed finite but large C, where a lot of people take C, like a series of CFTs where C goes to infinity, and then for them it's not possible to, for time to be bigger than C, but I'm taking fixed finite but large C, so it's possible for time to go over C. Yeah.
Sorry, what was the last question?
I'm taking fixed finite but large C, okay. So it's possible for a time to be much bigger than exponential of C, okay, which is what is required for to localize onto a single factorized state.
And in some sense, the billing is like not letting time to.
Yeah, but I'm trying to like make it formal. Yeah.
But I mean, you could have, you wanted to write this, but you could have just said I project. There's a projection operator.
What?
You just said I'm going to project onto this state. Right?
But I wanted to create that state using something in the code, like prove that the statement of the code subspace.
But if you
I just wanted a particular function, took a particular function of the left stress tensor, which gave me a factorized state.
Right, but I think the projection operators can all be built out of descendants acting on primaries. You choose some orthonormal basis and you do it.
Yeah,
And
yeah.
Therefore, you know, it will do the job. I'm just saying. And you
Oh
can-
no, I don't. Wait, yeah, you have to. This is one way to build it. Maybe there are other ways to build it.
I think, given how you've chosen everything, we could have done it.
Perhaps, yeah.
Your code subspace is all temperature states there.
It has all the temperature states.
So when you do it in the bulk, what boundary conditions are you putting? Empty conditions.
Oh, wow.
You're not fixing temperature. You don't have area because
Yeah.
so
No, I don't have information theoretical area.
you still have some.
You could like I will show that there's some in nice subspace where area is non-zero. Like the point is because I have factorized states, right? Factorized states don't have a wormhole between them, so there's no like the RT surface for a factorized state is just an empty set.
Okay, so I just want to know what boundary condition besides this code subspace in the bulk.
I defined it precisely for you, know, like what was imprecise in my definition.
You said
He's asking about the bulk. At the moment, there's no bulk, right?
Yeah, there's no bulk. In fact, I haven't taken large C also yet.
Right? At the moment, it's a field theory construction.
Yeah.
We'll see later.
Yeah, exactly.
Let me ask you one thing. I'm sorry, I have to leave around 1:15 today. But what is the plan? Since we have 3 lectures,
Yeah, I can.
more. But can we?
I can stop now and then we can.
You read some.
Okay, I will write down an equation. I will write down an equation, and then we can stop. So the Shannon entropy of these O's, which is going to be in the entanglement of psi, can be written as the Shannon entropy over the alpha, okay, plus the Shannon entropy of O given alpha, okay, there's something called conditional entropy, minus the Shannon entropy of alpha given O, okay.
I followed you completely up to here. Now it's
No, but wait. I am making I will explain the statement tomorrow. I just want to give you a preview of what is going to come.
Are you going to change your code subspace?
No, let me make a statement. Okay. I'm saying that you can write down, this is basically the log of base theorem, okay, and it's some relationship between various Shannon entropies. This Shannon entropy is there in SE of psi. Okay, the Shannon entropy of O's. It's a term in the entanglement of psi. Now this guy,
With the Shannon entropy, whatever it is, it's a function of the state you're looking at?
yeah, because it's got the POs. Now, just give.
So just to be clear, Ronak, I think what you're going to calculate is the entanglement entropy on one side
of psi.
of psi, and that's going to be related to the Shannon entropy.
It's going to have a term which is the Shannon entropy of O. Yeah.
That's what you're expecting.
Yeah, and I'm just writing down a particular thing. Okay, so the point is n alpha is going to be the sum over O f alpha of O. It is the effective number of states inside the bin. Okay, and there are two correction terms here. Okay, these two correction terms will measure how good the binning is. Okay, in a precise way, in a semi-precise way, and this term can be written as the expectation value of an area operator. Okay, of some new area operator, which I will write down tomorrow. And yeah, the point is that and these two terms being small will be the condition of having a semi-classical state, and importantly these two terms being small will be a non-linear condition on semi-classical state, not a linear condition. Okay.
Sorry, just let me understand this. Each of O is one.
Is the Shannon entropy of over the variable O.
Okay, but was H of O by definition minus
P O log of P O?
0 log P0?
Yeah.
Okay.
And H alpha will be like T alpha log P alpha.
What was the sum in the first formula? Sum over P0
Sum over O.
and H was an argument
H means Shannon entropy.
and of
So H of O means Shannon entropy over the O variable. H of alpha is the Shannon entropy over the alpha variable.
oh I see.
This is the conditional Shannon entropy, and this is the other conditional Shannon entropy, which I will define tomorrow. Okay, I just want to like give you a preview of where the area operator will come from.
And is the rough idea this that the probability P0 as you wrote down here actually
No.
is equal to the probability that you which way did it go?
So basically,
Go ahead. The probability to in the bin alpha to find O, P alpha 0 is the probability.
PO is the total probability to find O.
times
P0 times that the probability that you came from the alpha.
Yeah,
Yeah,
it
yeah.
came from
Yeah, yeah.
given P0
The fraction.
times the probability that if you are
If you have P0, what part or what fraction of P0s come from the alpha?
Yeah. Yeah. Anyway, we can. Yeah. So the point is that there's a joint. The point is that these two error terms will measure the two following things. The first one will measure how much PO varies within each bin.
how much?
PO varies within each bin. Okay. If it varies a lot within the bin, then that term will become big. Okay. The other term will measure how many alphas sit on a specific O. Okay. If too many alphas sit on the same O, which means the bin is too wide, then this term will become big. Okay. And so and then I'll argue that these are exactly the conditions on the state being semi-classical. Okay.
But you're not diagonal in alpha anymore, right?
It is diagonal in alpha.
Why?
Because
You could have had O1, O here, but could you get that from alpha prime?
Good. This is at the level of the state, which I will get to later, and there will be an approximate diagonalization in alpha.
H alpha is the Shannon entropy associated with what?
Hmm?
What is H alpha?
H alpha is the Shannon. So P alpha is going to be sum over O P of alpha O. Okay, it's going to be the marginal entropy on alpha, and the Shannon entropy of that is that.
Is this statement independent of the state?
This equation is a fact about probability distributions. Okay. Now the meanings of various things, like this thing being small, this thing being small, is dependent on state. Okay, it will demand these things being small will be semi-classical conditions. Yeah. So
The statement will hold for any state.
this thing is just a fact about probability. It's just Bayes theorem actually. Okay, I just took a log of Bayes theorem and then integrated it against. Yeah.
You take a delta function in O. If your state was O with O.
Yeah, if a delta function is O, that means that this term will become big.
But your state was a sum over delta function times delta function. Right? Now you can take that delta function and decompose that somehow in alphas.
Yeah.
But you get one decomposition on this guy, one other on this side. So it seems to me that you have off diagonal terms.
I will argue that there is a way to make the off-diagonal term small.
Okay. So what is the problem with off-diagonal term?
What is this?
Yeah, he is right that in the terms. Yeah, he's right that there are going to be off-diagonal terms, and there are going to be like cases where the left and right horizons have slightly different areas.
Are you saying that if the binning is very small, then this is the approximation where there is no off-diagonal term?
No, no, the off diagonal issue has not come to at all. Shiraz saw ahead.
The states that you're looking at are always diagonal, right?
In O.
Yeah.
But that doesn't mean they'll be diagonal in alpha. You have to do something to make them diagonal in alpha, which I will do tomorrow. I'll make them very, very close to diagonal in alpha.
But I'm also confused about if they're diagonal in O to begin with, and alpha just P of alpha over there, just sample some of them, they are always diagonal.
No, he's right, but we'll get there, because it's a difference between thinking in terms of density matrices and in terms of states. Shiraz is already thinking in terms of states, whereas I was like trying to talk about density matrices.
So you are writing.
Yeah.
You're writing this original integrated entropy as a sum and then interpreting various terms.
Yeah.
As indicated by the previous.
Yeah. And this log n alpha, by the way, will be the Cardi formula. It will be, if you take each bin to have order 1 width, log n alpha will be like the Cardi formula. Which it was a Cardi formula for primaries, which is slightly different.
From the usual.
Yeah.
Is this binning sort of like what Shrideep does?
In fact, yes, the fact that log n alpha is the Cardi formula is something that the best version is proven by Shrideep.
Are you going to use the same mathematics?
I'm just going to cite them. Okay. Yeah. I do need to prove certain things that they have not proved yet, but for what I'll say to tomorrow, what they proved is enough.
What is chi alpha in this case then?
Chi alphas are going to be like some particular. We'll get there. Yeah, I'm going to get to the state via the density matrix. But right now, I'm just want to argue that look, see this term here, log n alpha is just a property of the bin. So the state is only turning up in this p alpha, okay, and therefore it's linear in the state. Something linear in the state is the expectation value of an observable, which is why this is going to look like an area operator. And yeah, this is just how it is.